Assalamualaikum. Today, me and my group members will present our case study related to linear algebra. We are from CS112, Diploma in Actual Science, Group A4CS1124C. Our group members are me, myself, Nur Anis Adriana, Fahmi Rohaizat, Muhammad Azri, Ahmad Kofi, Natasha Alia, and Putri Nur Amirah Akilah. The title of our case study is The Implementation of Linear Algebra in Mario Games. As for the introduction of case study, we choose a topic from linear algebra which is vectors. Vectors are used to store position, directions, and velocities in video games. Video games are one of the most popular forms of entertainment. Thus, we want to learn on how linear algebra can be implemented in video games. Therefore, we choose Mario, since it is one of the famous fictional character in video game among people. Mario games have the ultimate goal, which Mario have to rescue Princess Peach after she is being kidnapped by King Koopa. These Mario games pass over the world that contain a set of number of levels for Mario to complete. Mario must complete the level in order to reach to the nest, which usually marked by a flagpole. In these games, Mario has many movements in order to complete his goal, specifically running, jumping, and duck sliding. The purpose of case study is to implement the use of topic vectors in linear algebra in Mario games. Second is to discuss some Mario moves and to know how Mario movement works based on the calculation from linear algebra.
Next, methodology. Firstly, vector addition. To add vectors together, you just add each component together separately. For example, the first component 0, 1, 1 plus with second component 2, 1, 2, you will get 2, 2, 3. Why do we want to add vectors together? One of the common application in games for vector addition is physics integration. Any physically based on object will likely have vectors for position, velocity, and acceleration. For every frame, we have to integrate these vectors that is add the velocity to the position and the gravitational pull to the velocity. However, by using this vector, we also can get some points of movement that move forward.
For our second methodology is subtraction vector. Subtraction works in the same way as addition. Vector subtraction is useful for getting a vector that points from one position to another. For example, let's say the Mario is standing at a point and wants to move at some point. To get the vector that Mario needs to travel to arrive at the point, we can subtract the Mario's coordinate with the point of this destination.
Okay, now we proceed to scalar vector multiplication. When we talk about vectors, we normally refer the individual numbers as scalars. For instance, we take 5, 6 as one vector and let the scalar equals to 2. Generally, in games, it is often useful to use the multiplication method by multiplying the vectors given with the scalar together. For example, we can try to replicate the basic air resistance by multiplying the player's velocity by 0.9 for every frame. To solve this, we just need to multiply the value of the vector by scalars. Let the player's velocity equals to 20 and 10. By using scalar vector multiplication, the new velocity will be 18 and 9 because we multiply 0.9 with the 20 and 10.
Next up, result. There were 3 problem statements. For the first problem statement is Mario jumping. In this problem statement, we use vector addition by assuming starting position of the corners of the box are 0, 0, 0, 1, 1, 1, and 1, 0. The starting velocity is a translation of 1, 3 with a gravity of 0, negative 1, which will be applied when Mario jumps. By referring the diagram, we see Mario first jump starting at the coordinate 0, 0. So, to find every of his position, we need to add his velocity translation 1, 3 from his position 0, 0 to get his new position when he jumps. So, to find his first frame, we let the new position as A equals to xy. Then we let his position as u, which is starting coordinate at starting point 0, 0. And we also let his velocity as v equals to 1, 3. To find the new position, we need to add his position with the velocity. And you may also refer this on the slide on the top right on how the calculation happened to get his new position. Moreover, we need to add his gravity 0, -1 to his velocity to find his new velocity, which is because when he jumping there will get gravitational pull. So the calculation is we let his new velocity with p equals to ab, then we let his velocity as v equals to 13 and the gravity 0, -1. So to get his new velocity, we add the velocity with gravity, or you may refer at the bottom right slide on how calculation did happen. In that case, we will get the new velocity 12. As we know just now, we get his new velocity is 12. So to get this next frame position, we need just to sum it such as the first frame, but with different velocity. We let the new position as a equals to sy, then we let his position as u with his coordinate at point first frame 13, and we also let his velocity as v equals to 12. We sum up his position and his velocity to find his new position, or you could refer on top left of the slide on how the calculation happened. As the result, we will get the second frame point 25. The process will be still the same after we find the new position, which we still need to find his new velocity. So we let his new velocity with p equals to ab. Then we let his velocity as v equals to 12 as his latest velocity and the gravity 0, -1. To get his new velocity, we add the velocity with gravity, or you may refer the bottom left slide on how the calculation did happen. Then we will get the new velocity equals to 1, 1. Then we will add the second frame position to get his third frame result, and the step is just the same as the step on the previous slide. At the end, the first jump result will be shown as a diagram. However, in this shown diagram, the second jump occurs. The calculation steps are just the same as the first jump, but the difference only the coordinates point. So here, we let the second jump occur at 6th frame. We add his velocity translation 13 from his position 63 to get his new position where he is jumping. We let the new position as a equals to xy. Then we let his position as u, which is at the point 63, and we also let his velocity as v equals to 13. Then we add his position with the velocity to get his new position, or you may also refer this slide on the top right on how the calculation will be happen. We will get his new position, which is 7th frame, 7, 6. Then we add gravity 0, -1 to his velocity to find his new velocity, which are just the same as the first jump steps. So the velocity is 1, 2. We add his velocity to his latest position 7, 6 to get his new position, which is 8th frame. To conclude, when the jump occurs, we need to calculate step by step with his starting jumping velocity translation 13 and with gravity of 0, -1 until the end of the platform. At the end, the result will be shown as the diagram on this slide.
Okay, now we proceed to the next problem statement, which is Mario ducking. As we can see, there's two diagrams that show the first diagram, which is Mario in a standing position, while the next diagram is Mario in a ducking position. So in this problem statement, I'm gonna explain how does ducking works in Mario games by using the application of linear algebra. Okay, as stated earlier, ducking in Mario's works with the application of scalar vector multiplication. During ducking, only y coordinates are affected because of y coordinates in Mario games represent the height. When Mario is ducking, his height becomes half from his standing position, and the x coordinate will remain the same and unaffected as well because of ducking in Mario only involve height but not the length. Okay, next, to calculate on how Mario went from the standing position to the ducking position, we firstly let the scalar equals to 0.5 and origin becomes 0, 0. Okay, so at point A, as we can see in the diagram of Mario standing, okay, the vectors given is 2, 2. So we multiply the vectors given with the scalar 0.5 to get a new vector which is at point A prime. So we get 2, 1 in the ducking position diagram. So the next one is at point B, the vectors given is 2, 0. So we multiply the vectors with the scalar 0.5 to get the new vector which is at point B prime. So we get 2, 0. So at point C, the vectors given is 0, 2. So we multiply the vectors given with the scalar 0.5 to get a new vector which is at point C prime, which is at 0, 1. So as we can see, it is clearly shows that only y coordinates are affected and x coordinates remain the same, because in Mario games, the ducking only involves the height, not the line. So therefore, it is shown that how scalar vector multiplication works in Mario games.
For our next problem statement, which is Mario movement. When we play the Mario's video game, Mario can either move forward or backward. Mario walking can be described as the vector addition and subtraction. We use vector addition to find Mario's new position as he moves forward, and we use vector subtraction to find Mario's new position as he moves backward. As a result, Mario moves forward. Based on the graph, it shows that Mario wants to walk from coordinate 1, 1 to a new position. To find the new position, we need to use vector addition. Let's say Mario moves forward 6 blocks away from his old position. By using vector addition, Mario's new position will be obtained, which is 7, 1. The calculation will be shown at the next slide. As the result, Mario moves backward. Based on the graph, it shows that the Mario wants to move backward from point 81 to a new position. We implemented vector subtraction for this case. Let's say Mario wants to move 6 blocks away from his old position. New position will be obtained, which is 2, 1, by using vector subtraction. The calculation will be shown at the next slide.
So next is we will see the coding of the calculation, what the codes do, what are the calculation, and the output of the coding. So we will see how the Mario jump, move, and ducking in the coding. Before we go to the calculation operation, we'll need to look at all the function that is in the coding. First is the void z. Void z is a delay function for the output in order to improve the UI display of the output. You will see how it will be presented in the output later. So next is the initial. Every variable that associate with the calculation will have initials such as jx, jy, dx, dy, and mx, my. The initial is defined: j for jumping, d for ducking, and m for moving. The third one is there will be 3 operations in the coding, and the output will also shows 3 operations. Okay, the first operation is jumping. We will see this is the snippet of the coding of jumping operation. The first one is jx new and jy new. It is the new coordinates of jumping x and y for Mario. It is included in an equation in order to calculate the new position of Mario using the coordinate in-game by adding the velocity of his movement and his old position. The next important point is new j val y. It is stand for new jumping velocity of the y-axis. As Mario jump, the gravity will affect the velocity of his jumping, and the calculation of the new jumping velocity of the y-axis will account the gravity velocity and the jumping velocity of y-axis. Now in the coding of a ducking operation, it is only contain cout. The ducking output only contain a printout of the shape of the Mario's hitbox. This is because the coding purposes is only to visualize how the hitbox of Mario shrink when he's ducking. And in the coding, it will draw the hitbox. The output will show a draw out of a Mario hitbox, and we can see the edges of the hitbox will have coordinates, so in order to visualize the shrinking when he is ducking. The last operation is the movement coding. The first one is mx, movex, and new mx. Mx is stand for movement x, which is operation movement, x coordinate. Move x is how many blocks he move in x-axis, and the new mx is for the new coordinate of the movement operation of x-axis. So we can see that the initial M stand for movement. The movement of the left and right of Mario in the game will only affect his x coordinate. The second one is addition and subtraction. The new coordinate of Mario in the game can be found by adding when he goes to the right and subtract when he goes to the left, just to simplify it. Using his old coordinate and how many blocks did he move from his old coordinate, Mario new coordinate can be obtained just by adding and subtracting. Okay, now we can see the operation of jumping. So when we enter the operation of jumping, we can see the original coordinate, which is before jumping, and the frame that will goes with it. So we can see it goes from 0 to 13 and 225 and 236. We can see that the y coordinate keep getting smaller. This is because the gravity is affecting on Mario jumping. On the left, we can see a video of Mario jumping. You can see that when he jump at the apex, it will goes back down. So that is the gravity affecting Mario to go back down to the ground when jumping. The second operation is Mario ducking. We can visualize Mario as a rectangle, and we can see how it shrinks. So the first one is there's a big rectangle of the, you can see the B and D y coordinate is 2. So when he duck, it will be shown to 1. And so in the video, we can see how it can be represented in game. If Mario didn't duck, he will be hit by the wizard spell. When he duck, the hitbox shrink. When the spell come through, it will not hit Mario because the hitbox shrink. Last but not least is the movement operation of Mario. So we can see on the output of the coding, we choose 0 coordinate and we choose 2 blocks to move to the right. We can see from 0, 0, it goes to 2, 0. And we can try it again. We put 0, 0 as the original position. Move 2 block to the left, we can see it is -2, 0. Because of when to the right, it will become an addition. When to the left, it will become a subtraction. This can be represented in the game by updating each frame of Mario movement. We can see that Mario is moving to the right in the game right now. So each frame, the game will update the new position of Mario by how many blocks did he move.
As for our discussion, there were 3 problem statements stated by my group mates, which are Mario jumping, ducking, and his movement forward and backward. For Mario jumping, we applied velocity and gravity into the calculation. The starting velocity coordinate is 1, 3, and it slowly decreased because of the gravity pulled it down, which the coordinate is 0, -1. Next is Mario ducking. We implemented scalar multiplication vector in this problem statement. The hitbox corners coordinates will change, affected the size of Mario will be decreased. Lastly, we use addition vector as he moves forward and subtraction vector as he moves backward. So in conclusion, maths is an absolute foundation to a successful game development and game design. Maths is everything when it comes to video games. Without the help of mathematics, a game would not simply work. A character would not be able to walk, jumping, or even sliding without the help of video games. The most basic games use some sort of maths to the most complex of video games. Mathematics is essential to the production of video games. Vector graphic is a linear algebraic way of storing and manipulating computer images. 2D vector graphics were especially suited to moving, rotating, and scaling images within retro games.
That's all from our group. Thank you for watching. And these are the references that we use in order to make the presentation. First, we use the website Canva for all the template that we use for the presentation. And songs can be found on Spotify. This is the background songs is Falling Asleep and Kingdom Blue. And last but not least, we use Tanner for the picture and GIF that can be found in the presentation. That's all from our group. Thank you.